So this is the 19th session on signals and systems, and we are going to study discrete convolution in this. So let us start. So first of all, we see how to express a signal in terms of unit impulses. So let us draw a specific example of a signal. So we got a discrete signal. So now remember that your independent variable is an integer and we denote it as n. And this is in contrast to the continuous time signals where your independent variable was time and that was expressed by using a floating point number. But for discrete cases, n is an integer. Note this. So if you look at this particular signal, note that on the x-axis n is plotted, on the y-axis amplitude is plotted, and that is your xn. So you can see at n equal to -3, its value is 3, n equal to -2, its value is 2, -1, it is 1, and so on. So this graph shows the signal. We have represented the signal graphically here. Let us write it in the form of a table. So at n equal to -3, this is 3 as shown here. -3 corresponding to 3. N equal to -2, it is 2.5. You can see 2.5. -1, this is 1, 0, this is 3, and so on. So this is how you show the signal graphically, and this is how you describe it in a table. Now further, we can also write this signal as a sum of weighted unit impulses which are shifted. So let us look at this. First of all, note that this is a specific sequence, but in general these values could be different for different signals. So let us write it more generally. So x -3 means that at n equal to -3, the value of the sample is x of -3. This means that at the value of n equal to -2, the sample value is x -2, and so on. So we have described it in terms of variable. Finally, you can write it in terms of the weighted sum of shifted impulses. So let's see how to do that. Now if you look at just one sample here, which is at n equal to -3, this single sample can be described as a product of x -3, which is this value, multiplied by the advanced unit impulse. Remember, unit impulse for discrete signals has a value of 1 at n equal to 0. And for all other values of n, it is 0. But when we say delta n plus 3, what do we mean? We mean that instead of delta n being 1 at n equal to 0, it is now 1 at n equal to -3, and for all other values it is 0. So when we take this product x -3 delta n plus 3, you are essentially representing just one sample value. All the rest of them are 0. Alright. Now when you take this term, which is the product of x -2 and delta n plus 2, this again represents a single sample value at n equal to -2, and for all other cases it is 0. So when you add them, you get this sample as well as this sample. So similarly, you take the product of each sample with the appropriately shifted unit impulse, add all these products, and you will get your xn. So let us write this in the more general form. So xn, now the signal that we had studied, it was starting from n equal to -3, but that need not be the case. It can start right from -infinity and go up to +infinity. So to show that, we have shown these dots here before n equal to -3 and after n equal to 4. Okay. So again, as before, we can write this as the sum of the products. So x -3 delta n plus 3 plus x -2 delta n plus 2, and so on. And this in general you can write by using a summation sign, where xn is sum of k from -infinity to +infinity, xk. Note this, see this -3 corresponds to one value of k here. and delta n minus k. So for example, when k is equal to minus 3, this will be minus minus 3, so that will be plus 3. Okay. Similarly, for positive values of k, for example, when k is equal to 1, this will be x1 and this will be delta n minus 1. So that is how you can write your signal as a sum of product of the samples and the shifted unit impulses. All right. So this is somewhat similar to what we did in the case of a continuous time signal. Only thing there we had used an integral to represent the signal because t was our floating point variable, continuous variable, expressed in floating point form in the MATLAB programs. But here it's a discrete variable, so xn can be represented as a sum. All right. So again, as before, we can develop the expression for the convolution by using the time invariance property of the systems and also the linear property of the systems. So for that, let us look at this table again. Again, this is analogous to what we did in the case of continuous time systems. There we had delta t and corresponding output was ht. But here you have delta n, which is the discrete unit impulse to the system, and we assume that the response to the unit impulse is h of n. Now, if you delay the unit impulse by k samples, then by the time invariance property, the impulse response, which is given by hn, is also delayed by k samples. So h of n minus k as we delay the input. Then if you multiply this impulse by xk by the linearity property, the output also gets multiplied. And finally, if you do the summation for all the input products, then you can do the summation for all the output products as well. So doing that, so we have put a sum here and we have put a sum here, and this output value now you call as yn. So what does it tell us? It tells us that if xn is given by this, which can be any general signal, then yn can be obtained by calculating this sum, and this sum is called as the convolution sum for the discrete signals. Okay. So this is the expression for the convolution sum. Remember, for continuous time signals, the corresponding analogous expression was an integral. Okay. So yn is called the convolution sum of sequences xn and hn and is denoted by xn star hn. Of course, as before, as in the case of continuous time variable, here also the order is unimportant. Even if you find hn star xn, you will get the same value. All right. So convolution of finite length signals. So we are going to study an example. But before we study that example, let us see what is the procedure for finding the convolution of finite length signals. Again, it parallels to that what we studied in the case of continuous time signals. So xn and hn are given. So what is the procedure? Rewrite the sequences replacing n by k, thus getting xk and hk. Remember there what we had done? We had replaced t by tau. That was our dummy variable. In this case, k is our dummy variable. Difference is that there it was a continuous variable. Here it is a discrete variable. Then invert hk and obtain h of minus k. So obtain h minus k by inverting hk. Then write down the sequence n minus k by choosing minimum n such that xk and h n minus k just overlap. So you are basically advancing this h of minus k towards the left, and if you advance it too much, there will be no overlap, there won't be any convolution. So you advance it towards the left just enough so that at least one value aligns. All right. Then calculate the sum of products of xk and h of n minus k. This is the first value in the result. Then increase n by 1 and recalculate giving the net value. Repeat until there is no longer an overlap. So this is the general procedure, and what we are going to do is to take a specific example and work it out. So let's say our xn is 2, 3, 4, 2, and we have used this arrow to show that this corresponds to n equal to 0. That means the leftmost index of this particular sequence, this is 0, so this will be minus 1, 1 and 2. So it is useful to know this, because after you have obtained all the numerical values for convolution, then you have to find out what is the value of n to the left end point and what is at the right end point. That is why we need to know that. So starting index of xn is minus 1. So this is 0. So clearly this is minus 1. That is also called as left edge of x, so LEX, or you can call it as the starting index of xn, which in this case is minus 1. Then end index of xn is 2. As you can see, this is 0, so this is 1 and this is 2. It is also called as the right edge of x, REX, denoted by REX. Then let us say that your hn is 1, 2, 3, 4 and n equal to 0 corresponds to this. So clearly if this is 0, this will be minus 1. Note, I am talking about value of n. These are the sample values. N is minus 1 here and minus 2 here. So in this case, the starting index of hn is going to be minus 2. 0, minus 1, minus 2. That is the left edge of h. And end index of hn is 1. So this is 0 and this is 1. So right edge of h. Alright. Having noted this, now what we have to do? First of all, replace n by k. Write your sequences again. So xk sequence is same, 2, 3, 4, 2. hk 1, 2, 3, 4. But now what you have to do? You have to invert hk. So you invert it, so it becomes, essentially you read it from right to left and then write it from left to right. That is a simple way of inversion. So 4, 3, 2, 1, and this n equal to 0 corresponds to 3. So here also it corresponds to 3. Now what you do? You shift h of minus k towards the left by a value of n which is minus 3, so that what will happen? See, you start from here, these two are aligned first. So 1, 1, 1. So 3 shifts. So when 3 shifts occur, you find that these 2 and 1 are aligned. None of the rest of the numbers are aligned. So when this is finite 4, 3, 2, these values are 0. So there is no product of sum here. Similarly, when these are finite, these are 0. So there is no product of sum here. So the only term is 2 and 1. So 2 into 1, that is h of minus 3 minus k into xk. This is equal to 2. That is what you get. Then what do you do? Then you shift to the right by 1 and again recalculate this. So when you shift it to the right by 2, so your n becomes minus 2, and now there are 2 overlaps. So you'll get 2 into 2, 4, plus 3 into 1, 3. So that is 4 plus 3, that is equal to 7. Then you shift it once more. So now there are 3 overlaps. So 3 into 2, 6, plus 3 into 2, 6, 6 plus 6, 12, plus 4, that is 12 plus 4, you will get 16. Like that you continue doing. Now I am not calculating all the rest of the values. I am sure now that you have understood this, you again shift it to the right by 1, you will get a complete overlap. You can calculate the next value of the convolution. Okay. So when you go through all this until there is no overlap at all, this is the result you will get. 2, 7, 16, 27, 28, 22 and 8. So now it's a question of what is the n index for the convolution value. And similar to the continuous time case, the left edge of y is the summation of left edge of x and left edge of h. So in one case it was minus 1, the other minus 2, so you get minus 3. Similarly, the right edge of y can be calculated as right edge of x plus the right edge of h. So 2 plus 1 is equal to 3. That is why this n ranges from minus 3 right up to 3. And if you want to find the number of samples, then number of samples in X plus the number of samples in H minus 1. So we had number of samples in this 4, remember, and number of samples in H also we had 4 minus 1. So you get 7 samples in the convolution. So you get 1, 2, 3, 4, 5, 6, 7. So this is one check you can use to calculate. So this is the standard classical method, that is, you invert one signal, slide it past the other. Very similar to what we did in the case of continuous time, but there we had to do integration over certain limits, and here you simply have to do summation as you slide the signal past. Okay. Now let me show you another method which is called as a multiplication method, and that is also equivalent to this, although I'm not showing the proof, but just understand the multiplication method. It will be probably easier to use this. So xn is given 2, 3, 4, 2. Hn is given 1, 2, 3, 4. So what you do is start from the rightmost digit. So 4 into 2, 8. Then 4 into 4, 16. 4 into 3, 12. And 4 into 2, 8. These are the values you get when you multiply by this. Then what you do, then you shift left once and multiply by the next number, that is 3. So you'll get 3 into 2, 6, 3 into 4, 12, 3 into 3, 9, and 3 into 2, 6. Then you again shift left, multiply by 2, so 2 into 2, 4, 2 into 4, 8, 2 into 3, 6, and 2 into 2, 4. Finally, you multiply by 1, so you shift left again, and since you are multiplying by 1, it is essentially copying this. So 2, 3, 4, 2, that is what you get. Now you sum up. So there is nothing here except one number, so you get 2. This 4 plus 3, 7. 6 plus 6, 12 plus 4, 16. Similarly, add all these to get 27. Add all these to get 28. All these to get 22. And finally, you got just one number, that is your 8. And note that LEY and NY are calculated as before. So we have seen how the convolution is calculated in the case of discrete convolution, and we have specifically studied the cases where our sequences are finite in length. And that is all in this session.